Hello, everybody. Today we're going to look at the concept of half-life. When you have an atom and the atom of a particular element changes its number of electrons, then the element changes. But if the atom changes the number of neutron, then you have an isotope of the same element. So you still have the same element, but you have a different number of neutron. The number of electrons and the number of protons remain the same. Radioactive isotopes have definite rates of decay over time. In today's lesson, we're going to look at the term half-life and how half-life can be used to determine the amount of radioactive isotope that undergoes radioactive decay over time. This is a very useful concept as it is used to determine how the number of disintegrations or decay over time changes. So the half-life of a radioactive isotope is a constant for that particular isotope. We're going to determine the amount of an isotope left after a given number of half-lives have passed. We're going to look at the graph of number of radioactive nuclei n versus time t for radioactive decay of an element. And we're going to see that the shape is pretty much the same for all isotopes. We're going to look at the half-life of an element, what it depends on and what it doesn't depend on. We're going to look at the activity, and we're going to look at how half-life is used in radioactive dating. Okay, so let's take a look at what is a half-life. When a radioactive material decays, the nuclei do not all decay at the same time. It is rather a random process. So we can't really predict exactly when a radioactive nucleus will decay. Although individual disintegrations occur randomly, we do see a pattern when we observe a number of parent nuclei that decay over time. So a radioactive activity, the activity of a radioactive sample is the number of disintegrations that occur per second. So every time you have a decay happening, the number n, which is a radioactive nuclei, that n decreases, obviously because it is decaying. So the activity can be obtained by dividing the number of nuclei that decays, which is n, so the delta n, over the amount of time that has passed. So the average activity over the time interval, delta t, is the activity of the radioactive sample, delta n over delta t. The unit that we use to measure radioactivity is called becquerel, BQ. 1 becquerel equals 1 disintegration per second. If you've ever seen those glow-in-the-dark watch, they glow they glow in the dark, and it's a very bright green. The activity of this radium is 4 times 10 to the power of 4 becquerel. The radiation treatment for cancer is about 1,000,000,000 times greater, or 4 times 10 to the power of 13 becquerel. Just a quick look back at one of our lessons about radioactivity. We looked at the work of Marie Curie and her husband Pierre, and one of the things that they used radium for is for paint. And there were in fact three. They were called the 3 deadliest colors. And one of them is radium green. So they looked at radium green, and they had lead, PB or plumbum. They had lead white and uranium orange. So these were the colors that they were using before, and they put them in paints, and they put them in all kinds of materials. And one of them is glow-in-the-dark paint that they used in watches. And these were the 3 deadliest colors because they were radioactive. So when a substance is radioactive, it is composed of radioactive atoms, and each atom has a certain probability that it will decay or release an alpha or beta particle and gamma rays. So think of it this way. This should have been an activity that we could do in class. If you have a bag of coins, let's say you have 1,000 coins in a bag. If I just randomly toss all 1,000 coins on the floor, chances are you're going to get 50-50 chances of being heads or tails. But if you only have a single coin, then the event is very random and you might get several heads or tails in a row. But if you keep doing this activity, let's say 1,000 times, the chances of you getting a pattern is likely. So it's about 50-50. Radioactive decay is pretty much like that. So although it is a random process, by observing many nuclei decaying, we can see a pattern. So it tends to be about 50-50. So that's basically what half-life is like. So if you look at the graph of radioactivity versus unit of time, the shape of the graph is called an exponent graph, or an inverse square, actually, like this. So this is the n and this is the time as it passes. And as you can see, you start at the beginning, you start with a lot of nuclei, and as you decay, as it decays, you get less and less and less over time. So the shape of the curve is actually called an inverse square. So for the coin, each toss removes half of the coin. So we can say that the half-life of the coin is each toss. Half the coins are removed with a toss. For material, it is when half the material has decayed and is no longer the original substance. This is a mathematical formula for calculating this physical phenomenon of half-life. So that n is the number of atoms remaining after decay time. The n naught is the initial number of atoms that we start with. And the exponent e to the negative lambda t, it's pretty complicated to understand. But we're going to be looking at this qualitatively, and we can still calculate the number of or what mass remaining after a unit of time. So this is that shape of the graph that we were looking at. Using the graph, we can determine the half-life time, or it can be determined from the equation. So we can either use a graph or the equation to calculate the remaining nuclei or the remaining mass as time goes. So let's do some. I'm going to attach a worksheet as well, but I don't have a printer handy at the moment. So we're going to look at some samples of the worksheet that I have attached to the blog as well. So let's take a look at some examples here. Example 1. So let's say that you have an isotope of cesium. So I'm going to look at cesium here. So cesium 137. So you have cesium 137 and the half-life. So let's say it has a half-life that is known, and it is 30 years for a half-life of cesium. If you start with 1 gram of cesium 137, 1 gram of cesium 137 over time, over a period of 90 years. Let's take a look at how many grams of cesium 137 would remain after 90 years. Well, one half-life of cesium is 30 years. That means, let's say you have this nucleus of cesium. That means for half of this to decay, it will take 30 years. So let's say we've taken out half of this, so that's decayed, and that takes 30 years. And then another 30 years for this to decay, so that would be 60 years already. And then so for that 90 years, that would be another half of this. So let's figure out how many half-lives have occurred. So 90 years divided by 30 years. So that means you have 3 half-lives that occurred here. So let's take a look at your starting mass of 1 gram. We're going to multiply this by 1/2 times 1/2 times 1/2 because you have 3 half-lives that remain. So what you're going to end up with is 0.125 grams left of the cesium after 90 years. And you started with 1 gram. Okay, so that's an example. Let's do another one here. So in our example 2 on the handout, we're looking at sodium 25. Now, if you look at sodium on your periodic table, sodium is 22.99 in its in the element of the periodic table. This is an isotope sodium of 25. Um, let's say you need to use sodium 25 in an experiment, but it took 3 minutes to get to the sodium from the reactor to the laboratory. So it took 3 minutes. If 5 milligrams of sodium 25 was removed from the reactor, how many milligrams of sodium 25 were placed in the reaction vessel 3 minutes later if the half-life is 60 seconds? So the half-life of this sodium 25 is 1 minute or 60 seconds, and it took 3 minutes. So how many half-lives have taken place? Well, you have 3 minutes, and half-life is 1 minute, so you have 3 half-lives have already taken place here. So we started with how many grams? So 5 milligrams. So you had 5 milligrams to start with of sodium, and you had 3 half-lives, so times half times half times 1/2. And so 3 minutes later, you would end up with 0.625 milligrams of sodium 25. That actually was number 3. I did number 3 on our handout, so I'm going to do number 2 now on our worksheet here. So going back, we have actinium 226. Actinium 226 has a half-life, I just call it HL, half-life of 29 hours. If 100 milligrams of actinium 226 disintegrates over a period of 58 hours, how many milligrams of actinium 226 will remain? Okay, so half-life is 29 hours, but this is 58 hours later. Oh. So 58 hours divided by 29 hours. So you had 2 half-lives have passed. So we started with 100 milligrams of actinium. And so 2 half-lives, half-life times another half-life here. And you are left with 2.5 milligrams actually of actinium. So this is how we can calculate the half-life or whatever mass is remaining. So whether we're calculating for the number of nuclei or the mass that is left after some time have passed, this is how we can calculate. We can figure out the number of if the half-life is given, we can figure out how many half-lives have taken place in that amount of time, and we can just figured that out by doing it this method. So I'm going to post the worksheet on Half-Life problems, and I'd like you to try that first. And I'm also going to post the answers right below that. So half-life is a very useful concept. And let's say they found a fossil somewhere, and they're wondering how old is this sample. um, we can calculate the radioactive decay of carbon 14 in an organic matter. So using this technique, we can use radioactive dating using half-life concept.